Hi, in this video we are going to look at solving a problem to get the pH of a weak acid solution. The example we're going to look at is solving the pH of a 0.15 molar benzoic acid solution given a constant, equilibrium constant of 6.5 times 10 to the minus fifth. Whenever you're looking at a weak acid solution, we want to look at the reaction associated with a weak acid. So our reaction, our generic reaction, we're going to use HA. That's just to represent any weak or any acid, plus water, and it's going to be in equilibrium. If I'm working with an acid, we remember acid is proton donor, so the hydrogen in my acid is going to donate to water, leaving me with the conjugate base, or A minus, plus the hydronium ion H3O plus. So we can now write a K expression. Remember, it's just K sub A, and the A just is meaning that I have we're writing it in particular for the above reaction, so this acid equilibrium reaction. And it's going to equal the conjugate base products over our reactants, just like the K's did in the earlier chapters. And we can write that as A minus our conjugate base concentration times the concentration of our hydronium ion all over the concentration of our weak acid. Because we don't include the water, because the water is a pure liquid, so we're going to not include that into our reaction. We're only including our aqueous components. The acid, the conjugates, and the hydronium ion. The goal, we're looking for pH. So the goal, we need to find something out about this H3O plus, because we remember the pH is equal to the negative log of our hydronium ion concentration. And so we need to be able to use these relationships in order to figure out that concentration of H3O plus at equilibrium. So shown here is the reaction for benzoic acid. This HC7H5O2 molecule is benzoic acid, plus water gives me the benzoate ion, this minus the hydrogen and the hydronium ion. Because we're in equilibrium, this K, we can look at this, and 6.5 10 to the minus fifth, that's pretty small. So if we're identifying our major species, this benzoic acid will be our major species. Our other major species is always the case when we're dealing with any of these acid-base equilibrium problems, is we're going to have water dissociation. And so water here is also a major species. We'll go to solve this, and we'll know that this reaction, the benzoic acid dissociation, is going to be more important than the water dissociation, because our Ka, 10 to the minus fifth, is much greater than Kw of 10 to the minus 14th. So we're going to focus in on our benzoic acid reaction. We're going to solve this using the ice table technique, initial change equilibrium. And from the previous page, the initial concentration of the benzoic acid that we are looking for was 0.15 molar. The water concentration doesn't matter. And then our ion concentration, our conjugate base, was initially 0.0, and our hydronium ion is 0.0 molar. Our change, everything here is 1 to 1, so And because we have no products at the beginning, we're always going to go to the right toward the product. So our change is minus x plus x for our product and plus x. And then we can look at our equilibrium concentration of 0.15 minus x, and x. We're going to put this into our Ka expression, which is going to be the concentration of our products over our reactant. Which is going to equal to x times x over 0.15 minus x, which equals 6.5 times 10 to the minus 5th. We'll use our small x assumption, at least initially, to solve this. Again, we'll always try to use this small x concept. We will validate it before the end of the problem, though. And initially we can think it is valid because Ka is still relatively small, 10 to the minus 5th. So we're hoping this is going to work out to our advantage. So we go to solve this and we get the equation x squared over 0.15 equals 6.5 times 10 to the minus 5th. And we solve and we get x equal to 3.12 times 10 to the minus 3 molar. Which is going to equal our H3O plus concentration. From here we can go on and calculate the pH using the formula pH equals negative log of 3.12 10 to the minus 3 molar, and we get a pH equal 2.5. We're not quite done. We need to validate our small x assumption. And we're going to do that by looking at the percent ionization, which is equal to x over the initial concentration of our acid, and that little subscript 0, that just means initial. And so we'll put in our x, 3.12 times 10 to the minus 3, all over 0.15. And we're going to multiply it by 100 just to get us to percent, and we get 2.1%, which is less than 5%. So we're going to use that 5% cutoff. And because of that, our assumption is valid. And so our pH of my solution is 2.5. So that's it. What's required to calculate the pH of any weak acid. Stay tuned for the next video where we'll be looking at pH of a weak base.